day, I'm Dr. T and welcome to my office. So in this video, I want to talk about safety, but I'm not going to do the classic don't lick the chemicals, at least not in this video. If you're in my class, almost certainly there'll be some kind of quiz or module about not licking the chemicals. It'll probably be phrased something a little bit more professional than that, like safety quiz or something. But in this section, I want to talk about safety from a little bit higher up level. Because traditionally we teach safety as this list of rules to follow, and there's a reason for that. If you have a good set of procedures to ensure that you're safe and you follow the procedures, then you'll be safe and you won't get hurt. But when we boil safety down into just a set of procedures and we forget the why we're doing them, we run into really two opposite problems, or multiple problems, I should say. There's the classic, rules are meant to be broken. And so I'll actually get into this. This is what we call normalized deviance, and that gets into this whole idea of we've got safety procedures, but sometimes we just don't do them. However, even when we do them, there's actually two ways that that can go wrong, and we need to kind of take a step back before we can look at that. First is that we can have safety procedures to protect us from things that don't exist. Every situation is unique, and sometimes we set up safety procedures to protect us from things. And if those things don't happen to exist, then we are doing work, we are taking extra steps, we are paying a cost and not receiving a benefit. And there's no reason to do that. Likewise, we may not actually be doing the safety procedures that we need to do. There might be a weird edge case where our safety procedures aren't actually meeting the needs that we have, and we would know that if we looked and did a custom set of safety procedures for what we were doing. In some respects, this is really the fear that I have, although let's be honest, you can imagine a situation where you're doing a bunch of unnecessary safety procedures. It's pretty clear that some of them are unnecessary, so you stop doing them, but you accidentally stop doing one that wasn't unnecessary. And once again, I'll get into this concept of normalized deviance coming in a little bit later. So the first part I want to talk about, what I'm going to call hard safety. And this is safety topics that are building those safety procedures. The second side I want to talk about is what I call soft safety. More of the derivative of the safety, the knock-on effects, and where the hard procedures can go wrong when we have a bad attitude about safety. I think I might want to call it soft safety stories that kill, because we humans like stories, and those can be dangerous sometimes because they can get us to do things that aren't real or aren't a good idea. The last part I want to talk about is recovering or responding to an emergency, because one of the things that I really need you to get the idea down is that we are going to try and make a bad outcome less likely. Less likely is not never. And so we can't get to a point where nothing bad will ever happen. As such, we need to figure out what to do if something bad happens and make sure it doesn't go too bad. So with that, I'm going to dive into the hard safety. I will say this other caveat for this module. Every class I do a safety module, and it's one of those modules where there's so much material I really want to include because I think it's really quite valuable. But it's also not the only thing in the class, so I can't let it get too much. So I have tried to narrow this down. It's still a lot of content here, but I've tried to cut back on the things that I thought I could cut back on. Obviously, everyone will disagree with me because they'll probably think I cut something that I should not have cut, or that I left in things that I should not have left in. But here is my stab at kind of a general overview of safety. If you want to dive deeper, you have a few options. I strongly recommend The Field Guide to Understanding Human Error by Sidney Deckert. Excellent book. Strong recommend that anyone who's dealing, well, just frankly, that anyone should read it. But definitely a good book for anyone in, say, engineering, STEM, or industry. Should definitely be reading that one. Truth Lies in O-Rings by Alan J. McDonald and James R. Hansen. This one is about the Challenger incident. You're going to notice the Challenger is going to pop up a couple of times. Alan McDonald was one of the engineers with Morton Thiokol on the Space Shuttle Challenger. And he was there when it exploded. So this is a kind of a primary discussion of what led up to the Challenger disaster and then the investigation, et cetera, afterwards. It's a good book. It is an incredibly long book. So I can't give it a glowing recommendation because it is really long. It's good, but it is really long. I have to strongly recommend the United States Chemical Safety Board's YouTube channel. If you like airplane crash investigations, these guys are the same thing, but with chemical plants and other chemical safety issues. Once again, this is great. This is when these things drop, I'm grabbing my food and I'm watching it over lunch or dinner or whatever. They're amazing. They're a must watch. So I strongly encourage you, check out their channel. This is my thing. I love their work. And if in the future, especially if you're going into engineering or construction and you really want to dive deep and put something on a resume, there are OSHA 10 and 30-hour courses, which take 10 and 30 hours respectively, that you can take. They're generally not offered through most universities. My school does not offer one to the best of my knowledge. But if you want to put something on your resume, some like construction foremen are required to take the courses. So they are going to dive in way more than I am going to even begin to scratch on a lot of the kind of nitty gritty on, you know, the don't lick the chemical side, both like don't lick the grinder, you know, that kind of stuff. Okay, so with all of that said, I'm going to dive into the hard side. And to do so, I want to talk about first an idea that comes from industry called the standard operating procedure. And the idea here is if you're going to do something, you kind of actually want to work out the best way to do it and then make a nice checklist and then work out all the safety considerations and so that everybody does the thing the best way and follows the checklist. And the reason you're doing a checklist is make it easy to follow. You know, if you think about a pilot, they've just like got checklist on top of checklist on top of checklist to fly the plane. That way you don't miss anything. You're not going, what do I do next? Oh, I do the whatever next, that kind of stuff. And it's very valuable, partially to make sure everyone's doing it the best way possible, but also so that you can evaluate what you're doing and what could go wrong. And here's an area where I want to bring up a couple of quick distinctions. First is a hazard versus a risk. And they're similar concepts, but they've got a key difference. A hazard is something that can go wrong and hurt you. So if you're chopping onions, the knife deflecting and cutting you, that is definitely a hazard. A risk is going to be the hazard multiplied by the likelihood. So if I'm chopping onions, the risk is actually fairly decent, especially if I don't have the sharpest knife in the world, because, you know, the onions have the layers and they separate and they slip, and I end up wearing a Kevlar glove on my left hand when I chop onions because of the risk. If, however, I'm, say, chopping bell peppers, they don't do that. Yes, I could miss and hit myself with the knife, but it's much less likely. They don't like to slip. So the hazard is roughly the same. I cut my left hand with the knife as I'm chopping my produce, but the risk is much greater on the onion just due to the nature of how an onion works. And so if I'm thinking about my risk, I want to assess the risk of everything I'm doing, everything in my standard operating procedure or, you know, dinner. And if my risk is maybe not where I would like it, I need to take a few steps back and go, okay, well, what do I do with this? And of course, if I'm chopping onions, you know, I got a Kevlar glove, I pop that on, I pop an exam glove on top of that to keep it clean from the food and vice versa. And boom. Hey, I slip, I hit my hand. Oh, well, it's got a knife-proof glove on it. So this is what we call a risk assessment. And we can make a risk assessment matrix. And in the matrix, we're basically plotting risk. We'll do hazard on one axis, likelihood on another, and you get yourself this nice little grid. And what you want to do is for every possible hazard, every possible bad outcome, stick it somewhere on that matrix. Now, things will gravitate to different locations, and when you're looking at things, you want to kind of prioritize the things you want to deal with. A saying my father used to have, he would go on about this in somewhat of a rant, but that is, if everything is top priority, then you have no priorities. Nothing's a priority. And so you need to prioritize your risks. So things on your risk matrix that are low harm, low likelihood, I like to call that the who cares corner, because it's not a particularly high risk. Your likelihood and the harm from the hazard are both low, so this is something that we can generally ignore. Maybe we want to deal with it if it's particularly easy to deal with, but it's not a priority. Likewise, if the harm is really high and the likelihood is really high, then this has got to be our first priority. The things in the middle, well, we need to prioritize them. We as humans are a little bit bad at risk assessment by vibes. We actually need to kind of look at this directly because we tend to think in terms of stories. And it's those things in the middle, the things that might be high hazard or high harm but low likelihood, or things that are very likely but low harm, ones where the risk is, when you take both into account, actually less than you might think. They might feel riskier than they are. The classic case is flying in an airplane. We have done, as a society, an incredibly good job of making commercial aviation ridiculously safe. Far safer than driving. And yet, flying, for obvious reasons, kind of feels risky. Feels a little bit dangerous. We don't quite get our vibe check in there. It's like, oh, it'll be safer just to drive 5 states over than fly. No, 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 no. It's actually safer to fly. Might be cheaper to drive. Probably is. But it's safer to fly. As humans, we want to make sure we kind of put our vibes aside and actually look at the risks and what they really are, because we are hardwired to look at some risks and things that we feel we can control easily and overweight those, and things that we just kind of seem random or chaotic and underweight those. Car wrecks, oh, those just seem normal. We kind of ignore those. Airplane crashes, oh yeah, they're on the news like crazy. Well, they're on the news like crazy because they very rarely happen. With this, I do want to bring in one set of terms as a dichotomy, and I'm going to basically ignore one of the two. And that is safety versus security. Safety is protection from bad things happening by accident. And that's the focus of this module. Security is protection from bad things happening from other people doing it on purpose. That was not an elegant definition, was it? But you get the idea. Security, you're protecting from bad people, whereas safety, you're protecting from bad accidents. Quite often, our needs between the two can be counterintuitive. So if you think about, say, securing your house, you want to lock all the doors. If you think about, what you would need to do in the event of a fire, ideally you wouldn't have doors. You would just run away. So quite often, some of the things you take for one way are going to be counterproductive for the other. And you want to acknowledge that and try and find a workaround between those two. Also, as humans, we emphasize the danger from bad actors a lot more than accidents. Okay, so I'm a chemist, and this is the part where I want to bring in an interesting idea. As we are doing our hazards, we want to actually be kind of reflecting on what our real hazards are. And sometimes we need to look at the hazards both in terms of quality, but also in terms of quantity. So something may have a series of hazards. It may be able to do harm, but the amount of harm may not be quite so fixed. And the classic case is dose response. So there's a famous quote. I'm going to have to read this off of my sheet. I have the handbook with me. That's what I'm looking down at. This comes from Paracelsus, who's a 16th century. It was quoted as 1538. I think that's 16th century. Physician, polymath, just one of those really smart guys kind of thing. He has this great quote that comes, it's actually in Latin, so this is a translation. All things are poison, and nothing is without poison. The dosage alone makes it so a thing is not a poison. Okay, that is not catchy, so we usually make it a little bit catchier of the dose makes the poison. Basically, everything is poisonous and nothing is poisonous. It's all about the quantity you consume. You can die from water poisoning. You have to drink a lot of water to do it, but people have managed to do that. And so what I want to talk about briefly is thinking when we're dealing with hazards, we want to think not only in the terms of how likely is the hazard to happen, how bad the hazard could be, but also like how bad will the hazard actually be? Because depending on what we're working with, the same accident could be very different in terms of outcomes depending on the quantity in question. And so in the chemistry, we think in terms of dose-response curves. This is actually a little bit more of a medicine side because they really have to think in this one. But this is something we definitely think in the back of our heads as chemists. And so the idea of a dose-response curve is on one axis, let's say the y-axis, we go ahead and we plot the amount of damage that's done, the amount of harm that's actually done. And then on the x-axis, we go ahead and we plot the dose, or how much of the thing are we being exposed to. So this would be, you know, how much of a chemical do you consume, or how much gets on you, or what kind of concentration. Obviously, we could split this into a multi-dimensional graph in terms of concentration and quantity. So we could vary this up a little bit, but let's just keep it simple. Harm on the y, amount on the x. And we could plot the amount of harm that a certain quantity of chemical or other property could have. You know, we could do the same idea with being hit in the head by a ping pong ball. Well, we would have, you know, the mass of the ping pong ball, the velocity of the ping pong ball, and how many ping pong balls, as well as where does it hit. So you could, once again, multi-dimensional graphing here, but same idea. I'm a chemist, let's keep with chemicals. And you could plot that. It would be some kind of weird squiggle, undoubtedly. So that would be a pain to sort out, and quite often we just don't have enough data, and we don't want to get more data because that means harm for people. So we can plot it out a little bit simpler. And the simplest one is what we call a linear no-threshold model. So in this model, what we do is we simply have a line going up. We figure out what the slope of the line is. We start at the origin, and we assume more chemical, more harm, or faster ping pong ball to the face, more harm. And this is generally a fairly reasonable approximation. I would argue there's very few things that truly fit a linear no-threshold model. And that's because as living systems, we have the ability to do repair. Our cells take damage all the time and they fix it. So as long as it's not too much damage, the harm really is canceled out by natural biological processes. But there are definitely a few things where you know what? It's definitely kind of, the no-threshold model makes a lot of sense to use. So little it doesn't really cause any harm at all is kind of hard to do. But on other things, it's pretty clear a small amount doesn't have any meaningful harm. And so in that case, we use what we call a linear threshold model. Once again, we're not going to try and do some weird curve. We probably don't have the data to fit a weird curve, but we do know that below a certain amount, really, the curve is pretty much just flat. There is no meaningful or no discernible amount of harm being done. So we'll just start the line off not at the origin, but down the x-axis away. That way, we realize as long as we keep it below that threshold, no harm is really being done. A lot of things really fit into this mentality. Now, there's actually a ton of different dose responses, and the more data you have, the better you can fit the line. I'm only going to show one more dose response. And that one usually is some kind of curve, and this one's going to be a little bit interesting, where you're going to have either no harm or possibly even harm at the zero dose. So that if you're not exposed to the material, it's going to hurt you. So obviously we could think something like oxygen or vitamins or food, etc., pharmaceuticals. And then if you're exposed to that, then it's going to dip down into hitting the no harm, or possibly even going well below harm and going negative. Of course, negative harm is benefit. So if you could think about, you know, a pharmaceutical, you're taking that to get a benefit. So no dose is not taking it, you're not getting the benefit. But if you take it and you take the right amount, you get a maximum benefit or the negative harm. But of course, if you take too much, if you put too much amount, it always goes up and you always reach more and more harm. And so you can overdose on whatever pharmaceutical you happen to be taking. So hopefully your healthcare team is trying to optimize and get the dosage right on track. So when we're thinking about hazards, we have several things to be kind of constantly thinking about, and we want to sit back and do that risk assessment and set up our matrix for every single thing we're doing, and keeping in mind, second and third order effects where there's like indirect harms being caused by things, as well as other variables like dosage. If I'm working with, say, some acid, the question is, am I working with 0.1 molar or am I working with 12 molar? That 12 molar hydrochloric acid, I'm going to treat that a whole lot differently than I do the 0.1 because its risk profile is very, very different. Now that we have our ideas of our risk, we understand what risk we've got in the activity we're trying to do, we now need to make a few more assessments. Because obviously the safest thing to do, the only truly zero risk, would just be not do something. But of course, there was probably a reason we wanted to do something. So now that we've done our risk assessment, we need to take a step back and we actually need to do another assessment for what we're doing. Now, depending on what we're doing, this might be a multi-page portfolio. Alternatively, this could all just be kind of in our head doing it real quick. Big thing, big portfolio, little thing, just, stick it in your brain. And this is going to be a cost-benefit analysis. And so we can imagine putting on one axis. This is actually like a multi-dimensional graph. So this is really more than one, but I'm going to cram this into one graph. We could have things like risk, cost, and effort on one axis. And then we could have, the benefit or reward or whatever positive things you're getting on the other axis. And we can plot where we hit here. So if something is not very risky and it's cheap and it's easy and it's going to give us some kind of great benefit, we're going to make a bunch of money or we're going to gain some benefit from this, well, this is a no-brainer. This is very much a just do it kind of thing. And so hopefully what we're working with is in that box. Alternatively, if our risk assessments come back that this thing is really risky, and, well, to be honest, it's going to be a lot of work, and it's going to cost a lot of money, and frankly, it's not really going to have that much benefit to it, then why are we even thinking about this? Let's just scrap it. We're done. We're just not going to do this. It's not worth doing. So we're going to avoid doing this thing. And that's a perfectly reasonable thing to do. It's quite often that we can get trapped into this kind of fallacy of completion bias where we just got to get her done. No, at a certain point, it's just not worth doing. The juice ain't worth the squeeze. Finally, the parts where you actually have to think. If something is risky and costly, it's got to take a lot of effort. Those are and/ors, I should say. So it might just be really risky, but cheap and low effort. But it's also going to gain you a lot of benefit. Then you kind of sit back like, okay. There's some downsides here. It's going to cost a lot of money, or it's going to be risky. I could get hurt, or I could lose a bunch of money or something. Or maybe it's just going to be a ton of work. But I'm going to get a lot of gain from doing this. Is it worth it? That's a hard call. You got to make that call. And sometimes the answer is yes, sometimes the answer is no. And sometimes the answer will be one way and you'll regret it. And sometimes you won't. That's one of those hard calls. The other end where there's really no risk or cost, but also there's no benefit, that is almost as hard a decision. And it's one of those where you can spend more time trying to decide if you want to do it than just doing it. Some business books I've seen in that category basically describe it as, well, if you got nothing better to do, you might as well do these low reward, low cost activities because they're like filler. But if you got anything else to do the other thing. Those are more worth doing it. So once you've done that, once you've done your cost-benefit analysis, you've assessed your risk, now you might be asking yourself, is the risk where I want it to be? Am I okay with the risk? Or is this something where, I would be very willing to increase my effort or my cost a little bit in order to reduce my risk, to make sure that bad outcome is less likely. It's never going to be impossible for it to happen. We can reduce it to incredibly unlikely, but we never get the bad outcome to 0. But we can get it close. So maybe I want to go ahead and, you know what, I don't like the risk. It's definitely not what I would consider to be acceptable. I need to move it down. I need to either move the likelihood down, or I need to move the harm down, or I need to move both down, and I need to get away from the, this is a problem, high priority risk, to hopefully into that who cares corner. So how am I going to do that? So the framework for this is called the hierarchy of controls. And this is traditionally represented as an inverted pyramid, kind of with the idea of the top of the pyramid is the best, and the wide part of the pyramid is the thing that is kind of like the dominant, what you use the most of. And usually it's like the low grade stuff, you have to do a bunch of it to support the high grade stuff. Well, in this case, the top of the pyramid is both the best and a really good approach. So the top of the pyramid is elimination. This is asking, okay, can I just get rid of it? I'm looking at my cost-benefit analysis. It's really not where I want it to be. Could I just not do this? Or if I'm looking at a procedure and I've got a step in that procedure, do I really need that step? Could I just not? Could I get my agenda done? Could I get where I need to go without doing the step? And so if the answer is, yeah, I don't really need to do it, let's just not do it. Or alternatively, it could be like, you know what, this is really not safe. Like, I still want to do it, but I can't do it without this, but no, I'm done. This is just, we're not doing this. So that's elimination. The next up is substitution. Okay, I don't like where the risk is at. I still want to do it. I can't eliminate it, but could I get something that's like it and replaces it? Sorry about that, light died. Okay, so if you're like me and enjoy watching various British nonfiction YouTubers such as Tom Scott, they will almost always have one episode where they gush overly about British electrical outlets. Their points are valid, however, they usually omit one non-trivial difference, and that has to do with substitution. So if you couldn't eliminate your hazard, you could try and substitute it for something a little bit less dangerous. So a lot of the world runs at 220 volts for household applications. Nice and efficient, you can get a lot of power to your electrical appliance nice and easy. And over here in the US, we do that for our high power appliances such as stoves and dryers. But for most household items, we do this weird quirk where we take the 220 and we actually split it into two separate 110 volt circuits. Now, we've cut the voltage in half. Remember that dose response curve thing I ranted on about and how it wasn't just chemicals? Well, voltage is one of those as well. If you get zapped, well, a high voltage means high harm, and zapped at 220, you're in a world of hurt. Zapped at 110, you're just hurting. So you'll probably be fine. Not necessarily, but you'll probably be fine. So we have chosen to do a lot of substitution for our electrical system, making it a lot safer for most of your circuits, not all of them, by dropping it down to 110 from 220. 110-ish. It actually gets surprisingly complicated on electrical outlets and voltage and whatnot. Okay, so that's your second approach. If you can't eliminate the hazard, maybe you could substitute the thing creating the hazard and it will have a lesser hazard. As a chemist, we've been doing this recently with methylene chloride. It's a classic solvent. It's a carbon, 2 chlorines, and 2 hydrogens on it. Works great. The only problem is it causes cancer and goes straight through gloves. And as such, new safety rules have come from the federal government that for most applications we can't use it anymore. I am not disappointed. I never liked working the thing to start with, although it made beautiful paint stripper. And what we're doing? Well, we still got to get the work done. we've replaced it with other chemicals that maybe don't work quite as well, but are a lot safer. Now, if you're sitting there going, well, I don't want to eliminate it, substitution is really not cutting it. Maybe I did substitute, but it's still not safe enough, or you know what? I can't substitute this out. It just doesn't work nearly well enough. There's no good alternatives. Then we can move into what we call engineering controls. And engineering controls are basically putting some physical safety device between me and it. And so that could be, you know, all the things that the British YouTubers like to talk about with their electrical outlets. How the one plug is longer than the others, and how they're shielded, and how there's a fuse in the base of every plug, and there's a switch on every outlet, and the whole long line of things. There's lots of things built into a UK electrical outlet in order to keep you safe from the 220 volts behind it. Some places will actually split up engineering controls into guards or barriers and then fail-safes. So the idea would be a guard or a physical barrier would be a piece of plastic or a piece of metal or whatever to keep you away from whatever's potentially going to hurt you. Think of some of the stops on a saw, that shield that goes over the blade when it's not in use. Whereas a fail-safe would be something that, if harm is about to happen, shuts things down, and so that it stops working in a way that protects you. They make these like things that shoot into the blade and destroy the blade of your table saw the moment you touch it. That way it doesn't cut your hand. You may get a nick, but it doesn't chop something off. So those are all under the category of engineering control, but some places do subdivide that a bit. Now, if you're looking at this one, you know, we still haven't gotten it safe enough. Or maybe you're looking at it like, I don't actually have that much hazard, so I don't need to eliminate it. I don't need to substitute it out. I really don't need any engineering controls. Maybe all I really need to do is tell people to not do something. You know, don't stick the fork in the electrical outlet, that kind of stuff. Well, this is what we call administrative controls, and these are split into kind of a couple of different categories, but in general, it all tells people how to do stuff in order to not get hurt. This is things like the, you know, don't touch the wet paint sign. Obviously, getting paint on you is not a particularly high hazard, but it's still quite unpleasant, and you just ruin the paint job. But also things of saying like, hey, when you are doing this, hold here, hold there kind of thing. That way you can't accidentally, you know, touch something that could hurt you. The classic example here, of course, are speed limit signs. Don't go above a certain speed. That way you're less likely to get in trouble and have a crash and get people hurt. Or if you do have a crash, you know, it's not going to be quite that bad. So we're substituting the speed from, you know, 200 down to 55, and we're telling everyone to do that. Of course, you can see why administrative controls is near the bottom of the pyramid. Yeah, you can tell people to do things safely, but they don't always do what they're told. Case in point, the speed limits, let's be honest, they're more of a suggestion these days. The last bit on the bottom is PPE, or personal protective equipment. Personal protective equipment is stuff you wear to keep you safe. This could be things like glasses, gloves, goggles that go over glasses, lab coats, etc. Generally speaking, for a large part of PPE, I sometimes like to think of this as kind of below ground. Like this part is actually kind of like, we're not actually where we want to be. Apart from things like gloves, if, say, your goggles protect your eyes, that's good, but that's not okay that it got that far, because that was the last line of defense. And as such, there was nothing backing it up. So if those had failed, you would be hurt. So quite often we consider PPE, for the most part, with exceptions of things usually like gloves, where if these if these are actually protecting you, that's not a success. That is a near miss. And we need to address and reassess the risk assessment because we had a near miss. But that also means that we need to focus on making sure we're using our PPE because they're the last line of defense. And if we don't have them, that means that whatever previous line of defense is now the last line of defense. Safety is quite often built like an onion. you do layers. If something gets through, an accident happens, and several layers get breached, hopefully you got one more. Alternatively, there's what's referred to as the Swiss cheese model of accidents. The idea is you got multiple layers of Swiss cheese, you know, the cheese that has holes in it. And as long as the holes don't all line up, you're safe. If the holes all line up, then you're in trouble. You can't get rid of the holes, but you could add more layers and hope the holes don't all line up. So the last part of hard safety I want to bring up is what's between your ears. You got a brain, and you are part of the safety system. Now, safety is quite often taught by a series of case studies, and I'm going to throw in a few. And the first one I'm going to bring in is referencing something that seems a little bit counterintuitive. If you go to a lot of, say, large national parks, national monuments, especially the really touristy ones, the ones that are like really cool, quite often you will have equestrian trails. You got a big open space, you're outside, kind of cool to pay some money to ride on a horse to see the sights. Yeah, kind of fun. Grand Canyon National Park is no different, except for you don't pay money to ride on a horse. Quite famously, you pay money to ride on a mule. Now, mules are famous. They're famous for being incredibly stubborn. You tell a horse to do something, the horse does it. You tell the mule to do something, and the mule is going to decide whether or not it wants to do something. So, I'm going to leave you with a bit of a question. When I ask it, pause the video, think about your answer, and then turn it back on. Why would this be a good thing? Why would it be a good thing to have an animal that is literally as stubborn as a mule? And I'll give you a hint. It's a safety reason why Grand Canyon National Park has mule rides, not horse rides. Okay, pause the video, think of an answer, and then let's discuss. You back? You got an answer? Remember, if you tell a horse to do something, they'll just do it. Tell a mule to do it, it will evaluate whether or not it wants to do so. Mules have a strong self-preservation instinct. So if you tell a horse to jump off a cliff, you're off a cliff. You tell a mule to jump off a cliff, the mule is probably going to stop and silently judge you for such a ridiculous command. This way, if you make a mistake, there's one more brain keeping watch out of whoever's on the mule. The mule. This is what we call intelligent disobedience. The term comes from the service animal sector, basically training guide dogs that if your handler asks you to cross the street while there's a bus coming, to just not. And this idea has spread into business and safety circles from there, where if you're in a situation where your superiors have told you to do something that is dangerous, immoral, or frankly just ridiculously expensive, then you don't do it. Now, the degree to which you just don't do it, of course, depends on what is the outcome. So if a superior is saying, hey, I need you to do a thing, and you're like, you know what, that is going to break a $100,000 piece of equipment, you want to make sure you send a strongly worded email going, dude, that's going to break a $100,000 piece of equipment. Are you sure for sure you want to do that? And if they are, then you do it, and the chips fall where they may. But if what you're looking at is something where there's a strong likelihood that it will kill someone or be a highly illegal activity, you don't do it. You quit your job. You tell them, no, I am not going to do that. In fact, I am going to resign on the spot if you want me to do this, and then potentially call law enforcement or the relevant authorities. I will warn you, whistleblowers are heroes, but they're treated like villains. No one's going to worship you as a hero if you're a whistleblower. It'll be quite the opposite. But you will be a hero if you are a whistleblower. Now, this moves into the category that I want to talk about is soft safety, or stories that kill. Where the hard safety, the setting up the procedures and thinking about them, we could have a perfectly good setup that's safe, and how it can go very, very wrong. And the way this goes wrong quite often involves just not doing the safety procedures. We've got a series of engineering controls, a series of guards, but they get in the way, so we take them off because it's easier. Or maybe there's some procedural controls, a subset of administrative controls where we do the procedure in a specific way, but you know what, we can take a couple of shortcuts. Well, there's a reason we did it a certain way. And we just get used to taking a couple shortcuts until all of a sudden, well, there was a reason we did it a certain way and a bad outcome happens. This is what we call normalized deviance. You're deviating from the standard operating procedure and it's become normal. This is like driving 20 miles an hour over the speed limit. Yeah, it's fine most of the time, but when you accidentally fall off a bridge, it wasn't fine. Now, once again, safety is quite often done by case studies, so I want to think about how we get to the world of normalized deviance. And this one, it's a little bit longer. I ended up writing this out. I normally don't do a script. This is me winging it, as you can quite often tell, going off my notes from the handbook. But this one's a script in the handbook, so apologies as I am looking down. I don't have a teleprompter. In the evening of January 27th, 1986, some of you know exactly where we're going on this. But in the evening of January 27th, 1986, there was an emergency meeting between managers and engineers of NASA and Morton Thiak. The launch of STS-51L had been scrubbed twice and was scheduled for a third attempt the next morning. But the temperature had dropped. Ice had formed on the shuttle. Morton Thiak engineers feared the seals on the solid booster rockets might not work at such cold temperatures. The booster rockets were made from multiple segments, and the seals between each segment made sure that the flame shot out the bottom and not out the side, and the engineers were afraid that they might not work. That would potentially result in an explosion, destroying the shuttle. However, the Morton Thiak engineers could not prove the seals would fail. They had never been tested at those temperatures. This was well below freezing. One had even triggered at 9 degrees. They didn't test it at 9 degrees. They'd only tested it at warmer temperatures. Without proof, NASA and Morton Thiak engineers gave the go-ahead for the launch. At 11:38 the next morning, STS-51L launched. 73 seconds later, the Space Shuttle Challenger was destroyed, killing all on board. What was the fundamental flaw on that January 27th? Because there was an idea in logic the night before that had killed those 7 people. Pause the video, think about it, and then come back. Welcome back. You probably caught the flaw. The engineers couldn't prove it would fail. That was the wrong question. They needed to be asking, could they prove it was safe? The Rogers Commission really dug into this, and this was the presidential inquiry after the accident. Neil Armstrong, who was on the commission, jumped in and was pretty much on the lines of, you did what? This is completely backwards. And this was, whenever we are outside of our known environment, we have to treat that as if it's more dangerous, not less. So we shouldn't be asking, will it fail? We must always ask, is it safe? Now, we still do the risk assessment matrix. Just because a bad outcome could happen doesn't mean we don't do the action, but we have to acknowledge the bad outcome could happen, and frankly, if it's destroying the craft and killing 7 people, that generally means you don't do it. You delay the launch. This ended up becoming one of the textbook examples of normalized deviance. So there's an interesting source of normalized deviance that I want to jump in and mention, and that's what's referred to as alarm fatigue. One of the reasons we might deviate from procedures is if those procedures are responding to some kind of alarm. If the alarm is a false alarm over and over and over again, you all read The Boy Who Cried Wolf, right? Well, if it's over and over again, we stop responding to it because we don't believe it's real. So when we're thinking about normalized deviance, we do always want to respond to an alarm, even if we think it's a false alarm. But we also want to make sure if we have any control over that alarm, that we avoid false alarms. Those are almost as dangerous as a no alarm when there should have been an alarm. When talking about safety, it's important to think about the organization and the group of people you're with and what we think of as safety culture. Safety culture is the attitudes and beliefs of the group towards safety. Is it safety is something we have to do on the side so we don't get in trouble, or is it we all want to make sure we go home? We want to focus on actually being safe instead of checking a bunch of boxes to keep somebody else happy. Because there's the old, what they don't know won't hurt me. Well, in this case, yeah, it might very well hurt you if you're skipping steps and engaging in normalized deviance. It's helpful to think about safety culture by thinking about the Aristotelian 4 causes. The idea was that something has 4 causes. The material cause, what it's made from. So if you have a table, the material cause would be wood. The formal cause, basically the design of the thing. So what is the blueprint for the table? The efficient cause, which would be someone built the table or how you manufactured the table. And then the final cause, which is why the table exists. So I want to have lunch. It's very easy to get caught up on the efficient cause, the rules and guidelines that we're doing to keep ourselves safe, and forget the formal cause. We're doing these rules and guidelines to keep ourselves safe so we get to go home, and we get to go home in one piece. So we're not hurt. Now, another interesting source of normalized deviance that doesn't come up too much. We normally think in terms of, shortcuts and trying to, make life easier or cheaper. A classic many disasters have been by cutting corners financially. But another one was discovered by a gentleman by the name of Sam Peltzman. I believe he is a professor or was a professor. I don't remember where. But he observed that the death rates in automobile accidents had gone down, but not nearly as much as they should have. See, this was the 1960s and 70s, and cars got a lot safer. But fatalities hadn't really dropped much. They'd gone down a bit for drivers, but for pedestrians who weren't even in the car, they'd gone up. And what he realized is that the cars felt a lot safer. And people were engaging normalized deviance. They were speeding faster. They were driving more recklessly because they felt they were safer. So sometimes we have to think about this second and third order effects. We can make ourselves safer, but if we feel too safe, then we can engage in normalized deviance. And, well, we feel safe, but, well, we're not actually safe. This leads to interesting things like roundabouts, which feel much more dangerous, but are actually safer because they feel more dangerous and everyone drives better. Side note, this is one of the reasons why I am not too aggressive with wearing gloves all the time. When you put gloves on, you're like, oh, I'm fine, I can't get a chemical burn, and then you touch your face. And, well, you might have got a chemical burn on your hand, but now you got it on your face. Whereas if you didn't have the gloves on, you've been paying a little bit more attention. Don't get me wrong, there's quite a few things that need gloves, but walk in, just put gloves on, you get used to just being all careless with the gloves. No. The gloves got to go on. You got to be thinking, I'm in glove mode. Now, this idea of feeling safe and our emotions, it's something that especially a lot of our more techie folks like myself don't like thinking about. But we have emotions. And when we're doing risk assessments and we're thinking about risk, we have an issue thinking in terms of feeling too safe and engaging in normalized deviance, or we can sometimes have other narratives in our heads that leads us to some rather interesting or counterproductive responses where we deviate from what we should be doing and move into some interesting approaches. Okay, so another case study. In this one, I'm going to have you pause the video and go visit a website. There is a very famous website called DHMO.org. It stands for dihydrogen monoxide. Go check out their FAQ page. Pause the video, check it out, and come back and see if you have some opinions on dihydrogen monoxide. Okay, welcome back. So, yeah, horrible chemical. Like, a major cause of death from inhalation, causes severe burns, a leading cause of brake failure, and it seems like there's a cover-up. It's a major component of naval propulsion systems. Yeah, how many of you all caught that it was water? yeah, the story, depending on how we present it, really can change depending on what it is. And so, one, we might be thinking a little too carelessly about water. Yeah, gaseous water, steam can cause severe burns. And if you inhale liquid water, well, that's called drowning. So you don't want to do that. And, it is a major part of naval propulsion. They're boats. When we're dealing with things we're working with, we want to make sure we get the stories right. We don't want to feel too safe, but we don't want to be panicking on things that just feel dangerous but aren't. And we can lead ourselves into doing things we shouldn't be doing, going away from safe practices if our stories aren't right, if our stories don't quite line up with reality. Now, I want to move into kind of one last spot, and that is a brief discussion of responding to emergencies. A lot of this is going to be very situation dependent, where you're at, what resources you have available. So I want to kind of keep this fairly open and broad. But emergency folks will quite often discuss the chain of response or some version of that. So emergency response chain of survival, that kind of thing. The idea here is some bad thing happens, you have an emergency, and people are affected. Now, there can be multiple outcomes here. We're going to go for a positive outcome. And, the most positive outcome is the person affected might very well be able to self-rescue. It's like, hey, I got myself hurt. I'm going to go to the first aid kit, and I'm going to get a Band-Aid, and I'm going to put a Band-Aid on it because I got myself a little bit hurt. Likewise, it could be a situation where a bad thing happens, and there's an automated response. Sprinklers are a classic example. Hey, the building's on fire. Oh, the one sprinkler pops off. By the way, they usually don't all pop off. That's a Hollywood thing. Unless you're in an airplane hangar or a chemical plant, they're not going to all go. But hey, all of a sudden the couch is on fire. Oh, wait, the one sprinkler. It makes a horrendous mess, but, a lot better than the whole building burning down. There's been classic cases where the sprinklers stopped the emergency. And then, of course, they're going to sound the alarm. Likewise, if there are bystanders, people in the environment where the emergency happens, then they can come help. Hey, if I'm in the lab and I get a chemical in my eye, I'm probably can't see. Hopefully there's somebody with me. And by hopefully, I mean like, if I'm doing anything where this could happen, there's somebody with me, or at least within screaming distance. And they're going to help me over to the iWatch station, and they're going to help address this, and they're going to call the emergency services. And that leads into the second chain of help. So no matter what has happened at this point, in order for there to be a positive outcome, unless the person can just self-rescue or the automated system can just remove the problem completely, which is usually not the case. But sometimes we can stop and the first change can just deal with the problem. But odds are we're going to need to call for help. And so the most important thing ends up being call for help. You got to call for help. And so now, once you call for help, a couple of things can happen. Most places, you're going to have emergency services. They're going to be coming. Firefighters, law enforcement, EMTs, that group, they're coming. They know what they're doing. They should be able to help you out. They'll take a little bit of time to get there, but they should be able to help you out. Likewise, EMTs are going to drag you to the hospital if need be. And, you got emergency physicians and the whole medical team over there. And that hopefully they're able to patch you up and you move on to recovery with more long-term solutions. Now, depending on where you're at, you may have what we refer to as local trained responders. This might be a group of employees that are trained in firefighting. That's not their day job. Their day job is whatever is going on. But you know that fire might be a big risk. And the fire department is maybe 5-10 minutes away, so we probably should work on putting it out before they get here, and then they can help us kind of thing. Or like, you're on a boat. Emergency services are days away, so you better be able to deal with everything yourself, kind of thing. So there is that other interesting local response. It depends on what you're doing. If you're remote, you're probably going to need those trained local responders. If it's particularly dangerous, you probably need them. If not, you probably don't have them. My school does not have its own fire department. It does not need them. So last couple of things I want to hit. So we've talked about chain of survival. or emergency response change, whatever you want to call it. I have one little case, and this comes from me kind of personally. In 2006, I was in Oxford, Ohio, Miami University, and there was an incident. And that was a Wendy's. We had a Wendy's there. And there was a gentleman doing work on the roof, was welding, so was doing hot work. And as does happen with hot work, sparks flew, a fire was caused. Obviously, there should have been more precautions, better engineering controls, but there wasn't. And so he goes downstairs, tells the manager, like, hey, by the way, the roof's on fire. And the manager evacuates the building, and everyone gets out. And a nearby meter reader, she's reading the parking meters. And she looks over and like, oh, the Wendy's is on fire. And so she calls into 911, like, hey, the Wendy's is on fire. And the fire department come, they put it out, and the thing was destroyed. And it was rebuilt a couple of years later as, I think, a burrito restaurant. But here's the interesting part. There was one 911 call. No one in the Wendy's, not the manager, not the welder, not any of the patrons, bothered to call 911. They just didn't think to do it. Somebody else will. This is known as the bystander effect. Somebody needs to do something, but everyone thinks somebody else is going to do it. I'd like to point out, you are someone. So if there's something that somebody needs to do it. It doesn't matter if it's done 2 or 3 times. If it needs to be done, get it done. Now, the last thing I want to kind of cover, so for this video, it's getting incredibly long. It'll be interesting when I edit this how long it actually gets. But I want to discuss consent. Because things change a little bit. And I want to empower you to be the person where if somebody needs to do it, do it. Normally, when we think about consent, if I'm going to engage with somebody or do something to somebody, like dump a bucket of water on their head, then I need to get an affirmative consent that they are willing to do that, and it needs to be an informed consent. So I need to go up like, hey, I would like to dump this bucket of water on your head. Are you okay with me dumping this giant bucket of water on your head? And if they don't say yes, you don't do it. But here's the thing, that's under normal circumstances. If there is a crisis, if you're in an emergency situation, if I'm on fire, do not ask me if I would like a bucket of water dumped on my head. Just dump the water on my head. Now, there are better ways usually to put out fires, good old stop, drop, and roll, don't get me wrong, but you get the idea. Now, that said, the informed consent doesn't actually go away. So, when you're responding to an emergency, questions usually go away. It's not, may I help you? It's, I am going to help you this way. Or, likewise, it's not, could you help me? It's, help me. You don't ask for help. You demand it. Because there's no room for politeness here. Someone's getting hurt. So this is like, someone is getting hurt. They may very well be incapacitated or at least heavily distracted by the flames, If you're in a situation where somebody's eyes are being burned out by a chemical, you don't ask them if they would like help. You start helping. But you tell them what you're going to do. Not knowing what's going on just adds more confusion and more fear. Not to mention, you need to coordinate with everyone around you. Hopefully, you're not the only person there. Hopefully, there is multiple bystanders responding to this emergency. And so, someone needs to take charge. No one's emotions need to get hurt. It's like getting your feelings hurt. No. We're going fast. We don't have time for these. I'm sorry. In this case, this is a bug, not a feature. We need to deal with those later. Someone needs to take charge and go, you, call 911. Remember, that call step in that chain of survival is absolutely critical. Then like, hey, we're getting you over to the eye wash station, or get the fire blanket, whatever needs to be done. And so start responding. If the person really doesn't want you to extinguish them, if they're on fire and they don't want you to put it out, they'll tell you, in which case I guess you would say okay. The caveat obviously is if they have unique circumstances where what seems to be emergency aid might actually cause much, much more harm, you want to avoid that. So Obviously if a person is in a situation where you need to help them, you help them, but if they tell you to stop, there's probably a reason they told you to stop. So respect consent, but move as an opt-out, not an opt-in form of consent. Obviously, if you think it's a situation, call 911. You don't ask for consent for calling 911. You just call. You can let them deal with it later if that needs to be. If it's bad enough you think you need to call 911, you're already calling 911. That kind of thing. So with that said, that wraps up this module more or less. I think I've got a couple of things I kind of skipped, but honestly, this video is getting way too long, so I'm probably just going to cut those out. And so with that said, I will see you in later videos, which are going to be hopefully a lot less dark, and have a wonderful day.